problem is a little more complicated, and first of all, let me read it, make sure it's readable on your screen. A large pump fills a tank in 4 hours. A small pump fills a tank in 7 hours. If the small pump breaks down after 2 hours, now they're working together, by the way, I forgot to add that in there. I'm shooting this at 11 o'clock at night, so I'm not too motivated to rewrite all this. But these pumps are both filling the tank. If the small pump breaks down after 2 hours, how much longer will the large pump need in order to finish? Alright, so you might try to visualize what's going on here. We have two pumps filling a tank. One goes faster than the other. And after 2 hours, the small one breaks down. How much longer does the large pump need to finish filling the tank? So I'm thinking about this. I'm thinking, well, how much have they filled after 2 hours? So in 2 hours, the large pump has filled. Then we multiply 2 hours times its rate, and it can fill a tank, one tank, in 4 hours. So you're probably thinking, well, that's half the tank, isn't it? And sure enough, because the hours units cancel, leaving tanks, so 2/4 is 1/2 tank. And the small pump has filled, what's it done? Well, in 2 hours, it pumps at a rate of 1 tank per 7 hours. So again, the units of hours cancel. There we get 2/7 of a tank. All right, so let's see what's left, because together this is, we have 1/2 a tank plus 2/7 of a tank. And let's add these fractions together. My common denominator is 14, so I have 14, 7/14 plus 4/14, 11/14 tank. So together in 2 hours, they pumped out most of the tank, 11/14 of it. How much is left? It'd be 3/14 of a tank left, right? So I'm going to have to do a little bit of erasing here to finish up this problem. Let me wipe out this top part here. Alright, so at least we have an idea what's left there for the large pump. Alright, so there is 1 minus 11/14. This would be 14/14 minus 11/14, 3/14 tank left. Alright, so this last little step is a little bit tricky. How do we figure out how long the big pump needs to finish pumping the tank? So we have 3/14 of a tank, and I'm going to write this as 3 tanks over 14, because this number in front of the word, the unit is a numerator. So let's make that a numerator. And the large pump pumps 1 tank every 4 hours. Well, what I need to do is to replace tank with the unit hours. So I'm going to kind of flip it over here, and in 4 hours it does 1 tank. So that's how you decide. And this is a point I've been making all along, is that the units are what decide the calculations in a word problem. If you're too stubborn to learn about units, then don't expect to ever be really good at word problems. And I know students who are very stubborn about that. They just want to, write equations and hope for the best. But the units really guide you in how to calculate a problem. All right, so look at this. See, the tanks cancel, leaving time, hours. And I end up with 12 over 14, which reduces to 6/7 hours. So it takes, and if you're my student, I expect you to write a sentence for a word problem. It takes 6/7 hours for the large pump to finish. For the large pump to finish. And there we go. It's done. So these problems, this previous topic and this topic, you notice I just wrote sentences and paragraphs and really explaining the whole process of solving these. And whether you write all that stuff out or not, it's up to you. But what's important is taking into account the units. And without the units up there, you're kind of working in the dark, and you can make mistakes. So, for example, I'm grading college algebra tests right now, and a lot of people made mistakes on this type of problem, on the rate, time, and distance problem, because they weren't thinking about units. In spite of everything I told them in class, they ignored me on that. And most of their answers were way off. So anyway, just again, if you want to get good at word problems, you got to think about those units. So, well, that was that one.